The only operation that can do something wrong is the widening. So essentially, if the widening includes something, like in case A, that leads to a non-terminated execution, we will actually see in the next step of the iteration, this part, so let's say this is undefined. If we do another iteration, we will go backward here, and since everything else is sound, since this state has successors that are not all in the domain of the function, this one will become undefined. So we will be in a situation where in the previous iteration we have a leaf that is defined. In the next iteration we now have a leaf that becomes undefined. So in the iterations, normal iterations, this shouldn't happen. We should always add the new pieces to the ranking function. So if this happens, we clearly are in a situation where we made the domain grow too much. So we will fix it by putting a top. So top here, you see the different rows between the values now. Top really means, okay, here we messed up, we did something wrong. This partition here can never become defined again. So bottom here can become defined because we are using the computational join in the iterations. But the top is at the top of the computational join order. So anything, we cannot modify it. When we reach top, this is immutable, we will just stay there. So this is how we fix it. And both bottom and top means that the function is not defined there. But this one, to the analysis, signifies that they can never, even if later on they figure out that they could actually have defined this function there, it's too late. Cannot be defined anymore. Good. So once you have done that, we can do the domain widening. And so the domain means we just grow the partitions on which we know that the program terminates. How does it work? It's basically, we do a unification of the trees, but now on the second tree, the tree that we found with the new iteration essentially, we will force the structure of the first tree. So essentially, what this domain widening does, it limits the number of partitions of the function that we are defining to a fixed number. At the base case, nothing happens, we are at the leaves. What changes is actually here, for instance, in the case, the constraint that we have in the second tree, so we have a constraint that has been added by the iterations. In the example, it was, let me see if I can show you again correctly. So all my yeah, this case here. You see, we had this iteration before, this iteration after. This constraint is added to the second iteration compared to the first. So this is a new constraint. So when we do the unification, we're going to compare this leaf here with this node. Okay? So let's go back to the... No, sorry, wrong slide. Okay, so in the second tree we have an extra constraint. We're going to remove it. And we're going to continue unifying, we're going to actually merge the subtrees doing the computational again. And then continue the unification for the rest. And similarly in the other cases. Yeah?
So what's the reason that we are prioritizing the left tree in this case?
Oh, it's just, well, the left tree is the tree that we found at the previous iteration of the analysis.
Okay.
So we're basically, it's certainly a tree that has fewer partitions. So we're going to say, and actually this is the simplest version of the widening version. We're going to basically say, okay, we're just going to restrict the pieces that we can handle in our function to this many, and we have to just figure out the value that works for the rest. So, I'm going back and forth between the examples, but I wanted to show you how that can work. I'm too far, sorry. So for instance here, you see this one, this constraint we said is extra, so we're going to remove it and merge these two during the computational job. And now, if you do that, this will basically say that whenever we are in this partition of the domain, the program will terminate in at most 5 steps, which is false, because we're also including the parts where y is negative. So we are being wrong, but it's okay. We will fix it later. Good. So back to the widening. Sorry, I should have done the examples one after the other. Okay. Okay, now what we've done with the domain, we're going to check for the other cases, the cases B or C. So these are the cases where we either underestimated the number of steps it takes to terminate, or we added states that are within directly onto an infinite loop. So in those cases, what we will see, it's what these lemmas are saying basically, what we will see is that at the next iteration, the value of the function that we had will have increased. Because again, everything else is sound. So here, for instance, we are at 2-step termination. If we do one extra step backwards, this will become 3. So at the previous iteration it was 2, at the next iteration this becomes 3. We will see that something is wrong. Same here, this is 2, we go back 1 step, this will become 3. So we will see that it has increased the number of iterations. So we can do various variants of this, but the course's case is basically say, okay, we have a function and the next iteration this function increases, again we put top there. We're going to say, well, something went wrong, we messed it up. We just forget about this partition. Okay, and then finally you can do the value widening. The value widening is basically trying to guess what is the slope of the function in the new partition that we have created. So for instance, we can be in a situation like this. This is the previous iteration. This is the next iteration. So essentially, at the next iteration, we have discovered this new partition that we have expanded to this part. And now we basically have to say, well, it's obviously not going to be exactly that same value that's going to work for every other state that we added to this partition. So we have to increase the slope in a way. And one way to do it is basically do some sort of an interpolation. This is at least one heuristic that we can use. It works well in practice.
It is okay for us to fill the gap because that gap was bottom and not top.
Oh, this gap here, no, I'm just, it's just an artifact because I'm considering integers, so the gap is not.
Oh.
But yeah, the idea is basically what I'm doing, it's how it is implemented at least, or how we can do it. It's basically, again, consider this as a polyhedra, consider this as a polyhedra. So then we're going to basically do this polyhedra and this polyhedra, we do the convex hull, this will give us this orange polyhedra here, and we keep this line on top, sort of. Or another way, you can consider it as an interpolation between this point here, this point there, this equal line that goes sort of in the same direction. Various heuristics can be used for this. This is one. So this is done by this extrapolation operator. So any implementation of the extrapolation operator is okay. In fact, you could replace, this is very trendy these days, you could even replace this extrapolation operator with an LLM. You can ask ChatGPT, okay, what should I put here in place? It's fine, it's totally fine. If it gets it wrong, it will get fixed in successive iterations. Okay, so we're done with the widening. I just wanted to talk about 1 second before we go back to the example, to the tree pruning mechanism. So the tree pruning is what we need basically to implement the assignment and the filter. And the idea essentially is that we're going to add a set of constraints to the decision tree. So let's say the set of constraints that we're adding is empty. Our tree will remain the same. If it's a leaf, if it's a tree with a constraint, we have to check if the constraint now has become redundant because of the constraints that we added already. In the other cases, we have to basically add the constraint in the order in which they should be. So we have to add them at the right place. So we always have to get the smallest constraint that we get from the set of constraints that we want to add, and we have to compare whether it should go before or after the constraint that we already have in the tree. So for instance here, the smallest constraint in J should go before this constraint C, and if it's not redundant, then we're going to add it and continue down with the pruning. And when we add it, you see we add these nil nodes. So in fact, it's the pruning that is responsible for adding all these nil nodes that will disappear later. When we prune, we just created these placeholders that are typically then filled when we do the joins. So we have various cases, but we don't need to go into the details. I just want to show the example. So for instance, here we have this tree. Again, try to go on this side as well. We have this tree here, we add this constraint. This constraint should go before any of those, so we add it at the root. We're going to put a placeholder on the right-hand side when the constraint doesn't hold. And for everything else, you just keep whatever tree that we have here as a such. Okay, now the assignment, how it is implemented. Well, it's a bit messy the way I wrote it, but you don't need to read to the whole thing. But the idea is basically we have to do the assignment essentially on the okay, we have to do the assignment on the variables, and then we have, because this function that appears at the leaves, essentially, will maybe contain variables, and maybe contain the variable x. So we have to do the substitution, essentially, of the expression into the variable x, also within the leaves. So for instance, down here, we have a function. Let's say this is the function. The function is x plus 1. And now we are modifying the function to do x gets x plus some choice between 1 and 2. This will give us, as a result, x plus 4, because essentially we are taking the function, we are replacing x with x plus 1 or 2, and then if we do all the replacement and substitutions, this will give us x plus 3 or 4, and the largest function, because again we want to have a linear function that is larger than all possibilities, is going to be 4. So that's how we get 4. This is for the leaves, right? So the leaves, we do the assignment on the function. For the nodes, we have to essentially do the assignment on the constraint and on its negation. Because again, the assignment, actually I do have an example later on, you will see it. But essentially, if an assignment is like this, we could actually get different constraints when we replace the constraint or its negation. Actually, I want to show you the example, so I will move to the example myself. It's in a totally different part of the slides, but I think it's useful to see. So this is a totally different part that we may or may not cover, we will see. But the idea, imagine that you are in this situation here. So you have this constraint on the tree, and you have this assignment that will replace C with some choice between 1 and 2 and 1. So now you do the assignment of the constraint itself, and this will give you this constraint here, because you replace basically C with the values minus 2, 1, the range minus 2, 1. You do the replacement, and then you have to go back to a linear constraint. So by doing that, you have to go back to, you get back to this. You have to basically enlarge the function. I have a picture actually. Yeah. This will give you this part. So you see, you have the new constraint. We will only talk about this part, this subtree here, the left subtree, and for the rest there is a placeholder. On the other side, you do the negation. The assignment of the negation will give you this other tree here. So you replace the constraint, will give you this other constraint. And you see they're not the same constraint. There's this constraint here which is slightly below 0, and this constraint here which is slightly above 0. So there is some sort of overlap, and then one has to do the join well, not this joint, this is a different joint, but it's basically you have to merge the two trees together to figure out what happens in the overlapping zone. But okay, this is just to show you why we need to do the assignment on one side and the other. Okay, and then depending on what sets we get as a result of this assignment, we may have to merge the trees or not. Or we basically if they're empty or non-empty, if they contain an unsatisfiable set of constraints, we don't know. Okay, this is whatever. In the normal case, essentially, what we have to do is do a pruning with the result of this assignment on the constraint itself on the left-hand side, and the pruning with the other constraint on the right-hand side, and then do the join, as I showed in the example. Okay, for the filter, this is the last operation. We're almost done. We have to first of all do the step, one step. And the assignment we also have to do the step. I didn't show you. But we have to basically increase by 1 the value, because we're counting one step termination. In the filter, we do the same. So we basically add the leaves where they are defined. So not where we have bottom or top, obviously. Where we have a function, we increase its value by 1 to count one extra step to termination. We convert whatever expression we have into a set of constraints, and then we use those to prune the tree. Good. So, with all of these operations, we now can define the actual semantics that will analyze problems and prove termination of these problems. So, for assignments, we just use the assignment operators. And this is sum in itself. For the if then else, we have to do the filter. So, we have to, it's a backward analysis, so we have to go through the, sorry. There was an if then else, okay, well, never mind, I will fix it. But the idea is basically we go through one path where the function is not true. Here we just do p. And the other path where the function is true, we have to go through the statement and then filter and then merge everything like this. Okay, well, there is some typos, I will fix them. And for the while, same as the filter essentially, but now we do it in a fixed way. Starting from totally undefined and then again also sound. This is sound because the widening does all of those steps to recover the soundness. Okay, for concatenations of statements, composition of statements, it's a backward analysis, so we start at the end of the program and go backwards. Also sound, isn't it? How does the analysis start? As we said, it starts from a function that is totally defined with value 0, and then we do all the operations through the program. And with this, we have that we can prove termination if the states are in the domain of the function. The states that we care about are in the domain of the function. It's not an if and only if. It's there's only one direction in the text. So we have this condition. Then we can say that it terminates. Vice versa, it could be that it terminates, but we don't have this condition. Again, because it's sound but not complete. So back to the example, we were at the widening, basically. So we were at this situation here. The widening here does something wrong, okay? The domain widening enlarges too much and says now this one has value 5. Okay, so the red part here is completely wrong. At the next iteration, we go back to the same situation as before, except that now here we have value 7. When we do the, so the case A is okay, we'll not see anything. When we do the left unification, the domain widening, what we end up doing is doing this. So what we will see is that we have a 5 here and a 7 here. So we are in the case where a function has increased its value between iterations. So we are in the case B or C. And so here we end up putting top. which means that whenever we did the mistake, now we're going to say we don't know, it's undefined here. And this is where the analysis stops for the loop. So we can only, in this particular case, because this widening is not particularly smart, in this particular case we can only say that the program terminates in one step if we never enter the loop, or in 3 steps if we enter the loop once. For anything else, we don't know. So we can actually, just to give you an idea, this was the very basic widening. We can actually do better. There are better heuristics for the widening. In particular, maybe inspired by this paper, we could look at the situation here where we have a triangle here and a slightly smaller triangle there. So we are exactly in this situation of, it's called an evolving rays kind of widening for polyhedra. We can do something similar here, which means that we enlarge the domain, but not too much. So in this particular case, when we have this triangle kind of situation, we should enlarge the domain up to the line here, which basically will take these 2 constraints, which are these ones in the figure in the paper, and will give us this constraint, which is exactly actually what we need in this particular case. So we're going to enlarge the domain exactly to where y is strictly greater than 0. Another question is how we do the value widening, because we also have to, it's not going to terminate in 5 steps there. We have more possible values for x. And here we can do the widening that we have seen before, where we increase the slope, and in fact we can get this kind of slope here, just by doing some sort of interpolation in the values that we have. And this is actually the best ranking function that we can find at this point. Good. So this is give you an idea of this domain for information. I think so. We could do ordinals, the extension with ordinals. We can do an extension to do other likeness properties. Which ones do you prefer? So let's say ordinals. Who wants to see the extension to ordinals? Okay, not many. The likeness other likeness properties. Okay, a bit more. Okay, fine, let's do that. Okay, so for other likeness properties, so this was for termination. Before we do that, quick thing, if you ever want to try, this is a very prototypical kind of tool. But yeah, there is a tool that does all this. It's on GitHub if you want. Roughly, it takes a program. You can specify a CTL property. It doesn't just do verify termination. It can verify CTL properties in fact. You can give it a precondition if you want. It's optional. And then it does the whole analysis. You can use different types of constraints. Essentially, interval-like constraints, octagon-like constraints for either and so on. You can use affine functions, the extension to ordinals. You have different widening heuristics and so on. My PhD student is working still on it, maybe unstable occasionally. But if you go back enough and you don't see his name, it should work. So, likeness properties. So we said, okay, termination is an instance of a guarantee property. So we can actually generalize this to other kinds of guarantee properties. And I want to show you also how it works for recurrence properties. The good things that happen in infinity ocean. To write this property, just briefly, I will just use CTL just because it's convenient. If you don't know it, it's a branching temporal logic. Essentially, it's a state-based logic. From a state, you have multiple different futures, and from a state, you can basically actually have a picture. For instance, from here, if you say this is, you have this quantifiers here. This is a universal quantifier or an existential quantifier. The A is the universal one, the E is the existential one. Essentially, it says from that state, talks about all the possible paths that you can take from there, and will tell you whether the property will hold, or where the property will hold them up. So for instance here, when you have A, G, phi, it means that always A, for all possible futures, this property phi will always hold. So the G means always. And instead the F property is the one that will say, okay, for all futures, eventually the property phi holds. So this is a guarantee property, essentially. Eventually we will get to a state where phi holds. And then this is the existential version of it. So here it's enough that there is a path where phi always holds, and here it's enough that there exists a path where eventually we get to a state where phi holds. I don't want to spend more time on CTL, but roughly, essentially, we're going to start with this kind of properties here, which are the guarantee property. So we're going to use, for the phi part, these are going to be state properties, or conjunctions of state properties. So essentially, some expression will hold eventually, or some expression will hold at a specific label of a program. So as an example, we're going to have, for instance, in this program here we just take, we read the variable x. Now we have a first loop that doesn't terminate. So neither of these loops terminate, okay? The first loop doesn't terminate, it just increases the value of x by 1, while x is positive. So if x is negative, we just skip this loop and we enter in the second one. And the second one just loops between 10 and minus 10. It just keeps going +1, +1 until 10, and then goes back to minus 10. In this case here, the property, for instance, always eventually x is equal to 3. This is true at the beginning of the program. Let's say, depending on the value of x, we may enter this loop. If it's not, no, sorry, actually, it holds if x is smaller or equal than 3 at the beginning of the program. If it's smaller or equal than 3, well, either it holds already or it will hold either in the first loop or at some point in the second loop. Yeah.
One sort of very general questions. So here we kind of always assume that there's no up or down, and there's no up or down.
Yeah.
You can see, of course, if you go like way up, it ends up circling back. Does that ever give you trouble with the verification?
Yeah, so in this particular analysis, for now, I'm just considering mathematical integers. If you want to be to work with machine integers, for instance, you have to actually consider the wraparound and all that stuff. So you would have to do sort of a wrapper around your domain to do it back. And actually, there are programs that, like this one here, will actually does terminate the machine integers. Okay, so for how we do the guarantee analysis, basically. Again, the semantics. It's very similar to the termination one. The difference here is now that here we are at 0 steps when the program has terminated, so at the end of the program. And here, the difference is that we are at 0 step whenever the property phi holds. So actually, instead of, I'll just show you the example, I think it will make more sense. Let's say we are in this transition system here. The orange circles are where my phi property holds. So this is where I start. And in particular, it doesn't matter if this state is within an infinite race. It doesn't matter. I just care that whatever in that state phi holds. So there, I am at 0 step to termination, and then it works backwards from there as before. So go back, I add to the domain of my function all the states that have all the successors already in the domain of the function, and increase the value of the function by 1. So here I add this one, one step to the phi property that I want. Here are 2 steps, and this is the fixed point. So similarly, basically, wherever my function is defined, then my guarantee property is defined. So it really is an extension, a very trivial extension of termination. And the analysis, I will not bother you with it, but essentially it's the same as for termination, except that now we have to do this reset operation after every statement, essentially. And what the reset does is basically wherever phi holds, we're going to put the function back to 0. Because we always are considering a state, wherever phi holds the property is satisfied already. So in particular, for a program, the analysis doesn't start with a totally defined function, but it starts with a function that is only defined where phi is true. And with that we have the same signs. Yeah. So
you just you assume that at some point phi is true, and then you backtrack on possible.
Yeah. Let's show you in the example, for instance. Let's say we want to prove this property here. Always eventually x will be equal to 3. I will spare you the analysis of the second loop. It's just too long. So this is the result for the second loop. So the function is defined everywhere with different values. And you see that the value changes depending on how far we are from x equal to 3 in this loop. Now we consider the first loop. So first we have to consider the condition. And the condition will basically cut away all the pieces that do not exit the loop. Yeah, I use this CFG sort of like depiction. I changed a bit the things, but yeah. So here, if we exit the loop, whatever function we had before only holds wherever the condition is true, so for exiting the loop. And now we have to do the reset. The reset will add also 0 where x is equal to 2. So there is one little dot and a very small that I added. Now I do the assignment. This will modify my pieces slightly. I do the condition. So I add the join with whatever I had from here, plus the reset again. So I had a point that was here slightly higher than 0, and now I reset it to 0. Okay, if I continue the analysis here, basically I will just add points until I reach the fixed point in this case, which is this one, which finds exactly the precondition that I need to satisfy this property. So I need x to be less equal than 3. Yeah.
Sort of conceptually, what is good about knowing this guarantee for the second? Because if we run this and we never reach the second loop, what's the use of knowing the arguments are somewhere that you don't reach? Is it because we don't know?
No. For the second loop, this will tell you. So what this function tells you is that from this point on, whatever the value of x, this property will always be satisfied.
Okay. So it's still useful to know, like, if we start here in the middle, we'll have this.
Yeah, but actually from here, if x is smaller than 0, you don't enter the first loop, you just enter the second one. So it does hold. So it actually keeps this part of the second loop in here, in the comment is still there. I think the more interesting bit is for the recurrence properties. So actually in the tool you can also find the part that does guarantee, but the recurrence properties are more interesting. Because these are the ones that where the property happens infinitely often. So in the example here, if you consider a slight variation of the property, and here now we say always eventually x is equal